Today our speaker is Chandrodoy Chattopadhyay. So he did his PhD from TIFR in 2019, and his thesis work was given honorable mention Rahul Basu Best Award, associated with our institute. So then he went on to do his postdoc in Ohio State University. He did very nice works there on hydrodynamic formulations, with maximum entropy methods, and then he's in North Carolina State University now as a postdoc. So, welcome.
Thank you so much. I'll be talking today about relativistic hydrodynamics and its applications in heavy ion collisions. So, heavy ion collisions at the Large Hadron Collider and relativistic heavy ion collider produce the smallest and the hottest droplet of liquid on Earth, with temperatures reaching almost trillion degrees Celsius or Kelvin. It doesn't matter at these scales. What is done in these colliders is heavy nuclei like lead or gold are accelerated to very high velocities, almost to the close to the speed of light, and then they are made to collide with each other. The collision energy per nucleon pair in the center of mass frame is so high compared to the rest masses of nucleons that these collisions are truly ultra-relativistic. Because of this ultra-relativistic nature of these collisions, these nuclei appear as thin disks, which then collide to form a region of extraordinarily high energy densities, which can be almost 20 times the energy density of normal ordinary hadronic matter. Because of this very high energy density, what happens is the fundamental constituents of neutrons and protons, that is the quarks and gluons, they become free over nuclear volumes rather than being confined within the protons and neutrons in the ordinary state. This novel state of matter has been called the quark-gluon plasma. What happens after that is the matter expands and cools, and even essentially because of Lorentz contraction.
That's a frame-dependent state.
But energy density is also a frame-dependent object.
But you will derive interactions out of it.
So
you will conclude something.
I will conclude something about the macroscopic nature of the liquid that is being formed. So as this medium expands, it cools down, the energy density decreases, and eventually the energy density becomes lower than that of a typical hadron, which is when the quarks and gluons, they recombine to form ordinary hadronic matter, which then free stream to the detector and are observed. So typically a heavy ion collision consists of several stages, which may be sketched as follows. Two nuclei come in, collide. It is the collision is characterized by an early time far from equilibrium regime. Then subsequently the medium becomes describable by hydrodynamics, which is the quark-gluon plasma stage. Then the quarks and gluons recombine to form hadron. So basically the density becomes so less that hydrodynamics can no longer be applied. So it has to be described by some sort of kinetic theory, and which eventually these particles, the hadrons, free stream to the detectors and are observed. So over the last 20 years or so, it has been established that relativistic hydrodynamics has been remarkably successful in describing the evolution of the quark-gluon plasma. However, typical hydrodynamic simulations use a starting time. This is the Milne time, these lines of constant Milne times in this picture. They use a rather short starting time, for example, less than 1 Fermi over C, and then evolve the fluid up to about 10 Fermi over C. Well, it is traditionally said that hydrodynamics is valid only when a system is close to local thermodynamic equilibrium. So then the question is, does this imply that the QGP that is formed in these collisions is in thermodynamic equilibrium for the entire duration of this time when hydrodynamics is describing it? Or in other words, does hydrodynamization imply thermalization? Or is it that this far from equilibrium stage where one should not traditionally apply hydrodynamics also has some similarities which can be described by hydrodynamics. But this is one of the question I'll be interested in throughout this talk. The other one is a feature of many body systems which hydrodynamics always ignores. Basically, the fact that the many body system at finite temperature always has thermal fluctuations in it. So this is another aspect that I will shortly touch upon in this talk. So for the first part, to say whether hydrodynamics is applicable even far from equilibrium, I will consider a simple system whose microscopic dynamics is described by kinetic theory, which is applicable both near and far from equilibrium, and compare its predictions with hydrodynamics in far off equilibrium regimes. And in the second part, I will talk about how thermal fluctuations may be included in hydrodynamics. So a brief review of what relativistic hydrodynamics is all about. So it is a macroscopic theory that describes the evolution of conserved densities of a system. For example, the energy density, the momentum density, or any conserved particle densities. Hydrodynamics is, the beauty of it is simple in one hand and also general. It is simple because all the complicated details of microscopic properties of the system that it is describing are captured only in a handful of quantities, like equation of state, which relates the pressure and energy density, and transport coefficients like coefficient of shear viscosity, bulk viscosity, thermal conductivity, etc. The hydrodynamic degrees of freedom are typically thermodynamic variables like temperature, chemical potential, collective velocity, which have now been promoted to fields of space and time. And when do we need relativistic hydrodynamics? So whenever the particles constituting the fluid have velocities that are very large or close to the speed of light, that is when we require a relativistic hydrodynamic description. So because we want to build up a relativistic theory, the description must be Lorentz covariant. So this is done by writing these conserved densities that I was talking about in a covariant notation in terms of energy momentum tensor and any currents. And conservation of these quantities locally implies these simple equations. Now, the main assumption of relativistic hydrodynamics is that these quantities can be expressed in terms of the hydrodynamic fields, basically the temperature, the chemical potentials, and the collective flow velocity. For example, in a fluid that is in perfect local equilibrium or an ideal fluid, the T mu nu takes a simple form given by this equation. We call it ideal or dissipationless because within this framework, no entropy is being produced. This is in Landau frame, but if I take a fluid which is ideal, then both the frame definitions match. So, but yeah, in this, throughout this entire talk, I will consider the Landau frame choice, which means that this flow velocity is the flow of energy. So it defines the flow of energy. Yes.
For completeness,
Yes.
why do I ignore the quantum fluctuation?
The quantum fluctuation. So this framework will define only the long wavelength dynamics of conserved charges.
Yeah,
Yes.
the couple of Fermi scales and distance.
Yes. So yeah, that is an assumption. In hydrodynamics, those short scale fluctuations it cannot deal with. So that is the nature of this is just an assumption. Yeah, indeed.
Here, when you say it's long wavelength, what is long?
Yes. So yes. So if I take any of these conserved charges, say the temperature. Okay. Now, if I put in a perturbation and see how it evolves, then hydrodynamics will correctly describe only those wavelengths which are large compared to the microscopic scattering length. It will, in principle, give us results for all wavelengths, but for the short ones, that will. So basically, by wavelength, I mean just the Fourier transform of the perturbation, and so.
So what
Yes.
Then where you can trust it?
Yes.
That's a your quadrupole plasma must be more than lens, right?
Yes. So there are essentially for hydrodynamics to be applicable, there are two length scales. So one is the microscopic scattering length, the mean free path, all that is required is the scale of variation of inhomogeneities should be much larger than the mean free path of the system.
Plasma that you create,
Yes.
is it big enough that you can apply basically what?
That is justified after doing the calculation because
The estimates already
we have estimates of mean free path by assuming some sort of quasi-particle model, but it is always a recurring question whether the QGP formed at temperatures of say 200 MeV can be described by a quasi-particle description or not. But
what is the size of that?
size of is about 10 Fermis, 7, 8 Fermis. Yeah. Yeah.
What drives you out of equilibrium in this case? Like, how do you start by saying that, okay, this is a non-equilibrium component?
Yeah, firstly, the system that is produced, it expands into vacuum. So it is not a system that is in a box which will stay in equilibrium. Even if you start from equilibrium, it will expand. So it is not something that is formed in global equilibrium. So it expands and goes out of equilibrium.
So it's not clear what do you mean that it expands and goes out of equilibrium.
So when you, okay, what I mean is that after a fluid is being formed, after that, it has some pressure because outside is vacuum, inside is matter. So then the pressure pushes the fluid out. So it evolves.
So you are saying that this is more like a gradient, you have a pressure gradient or something like that?
Yes.
I mean, because when I say non-equilibrium to non-equilibrium, I need an ingredient of non-equilibrium component, right? It could be affinity, meaning a disbalance in thermal temperature or pressure disbalance or something like that, right? Or
Yes.
maybe I could have a constant drive.
Yes.
Something like that. So what is this component you are putting?
So here it is spatial inhomogeneity that is already there during the creation. But even if we just for the sake of argument, assume that it's spatially homogeneous, still it's a finite system. So there is an edge. So it always has some gradients. So is that these are equilibrium properties in the sense of local equilibrium, not in global equilibrium. Just as if I have a box, I have some gradients, and I just let it evolve. So in that case, what would happen? Say I have some fluid which has whose velocity layers are different so like a shear mode. If I just let it go, all that will happen is because of friction, they will all move together. So it is because of this initial inhomogeneity that the system will eventually try to move towards that it is not in equilibrium, but it will eventually try to gain some sort of global equilibrium. In an ideal fluid, it will not go away. Whatever gradients are there, that will not dissipate into heat. So in this framework, this is this is the most simplest ideal kind of description. So their gradients will stay, but you are asking why it goes away or why should a system dissipate or what?
That's my first question. But
It is always in non-equilibrium. It is a local thermal equilibrium. Doesn't mean that globally. Always there is entropy in the responsibility.
So yes.
This is purely an equilibrium entropy.
Yes, this is not a function.
No, this is for the ideal. Of course, in a natural case, you don't have the ideal. So there are viscosities, gradients.
Environmental entropy.
Yeah, there are these gradients.
That will also come, right?
So, okay, what happens is, so this quantity S equilibrium, it is changing with time because it is the entropy density. But what we can show is the current, so this would be zero only in an ideal fluid and would be greater than zero if I have some non-equilibrium corrections here. But what I'm saying is all of these quantities, these ones, are functions of space and time. They're evolving because there is gradient in the system. Just that all these gradients are not being smoothened out by dissipating into heat. That is not happening in an ideal fluid. But eventually, I will put in transport coefficients where we will see that entropy is being produced and this, yeah. Okay. So if we do a little bit of variable counting about how many equations we need to solve hydrodynamics. So in ideal hydrodynamics, we have the energy density in the local rest frame, the thermal pressure, any conserved charge densities, and the fluid flow velocity u mu. So there are essentially 6 unknowns, and the conservation equations correspond to 4 coming from the energy momentum conservation and 1 from the any net charge current conservation, along with an equation of state which relates the pressure to the energy density and number density. We have 6 equations. There are 6 unknowns. So ideal hydrodynamics gives rise to a closed set of equations. But if there are non-equilibrium effects in the fluid, which has to be added in the description by adding these non-equilibrium stresses. This is the shear stress tensor. This is the bulk viscous pressure. This is the charge diffusion current. Then this gives rise to additional variables whose equations of motions we also need to formulate. So traditionally, these dissipative fluxes, which are shown in red, are expressed as a series in gradients of the fluid velocity. For example, the bulk viscous pressure is written as in terms of the expansion rate of the fluid times a coefficient, which is a bulk viscosity coefficient. And similarly, the other tensors can be expressed out in terms of gradients of the fluid. Now, I want to compute how these non-equilibrium stresses are related when I assume that the underlying system is described by kinetic theory. So let us consider a gas that is out of equilibrium. It can be described statistically using a single particle distribution function f, which gives the mean number of particles that are in a phase space volume element. Now, the connection between this single particle distribution function f and the conserved currents, which are the main objects of interest in hydrodynamics, are given by this. Essentially, here the assumption is that the kinetic energy of the particles are much larger compared to their interaction energy. So this is how the one relates the single particle distribution function to the conserved stresses. Now, and there can be more quantities. I mean, we can also look at non-equilibrium entropy and so on, which I'll come to later. So in kinetic theory, this main object of interest is this single particle distribution function. It evolves according to the Boltzmann equation, where this is the Boltzmann equation with a collisional kernel given on the right-hand side. This specifies the effects of interactions. Now, in general, the Boltzmann equation is a very nonlinear integral differential equation because of this collision kernel. But for the purposes that I am interested in, namely whether hydro can describe a system far from equilibrium, it suffices to choose a very simple form of the collisional kernel given by the relaxation time approximation. So here, I mean, all that it assumes is that all complicated interactions between the particles essentially result in driving the system towards a state of local thermodynamic equilibrium, where tau r is characterizes the microscopic relaxation time of the system. So, so given this collisional kernel, the next step is to solve for the distribution function f. We cannot still solve it exactly, but to solve it approximately, and then integrate over the microscopic degrees of freedom to obtain hydrodynamics. So that is the strategy at hand. So yes, so as I said, this u is the hydrodynamic velocity or the collective velocity. So what it does is, if we are in the local rest frame of the fluid, then u dot p is just p0, which is the energy. And then this equation would describe the relaxation of F to just F equilibrium. So this factor comes in because we want the system to relax to equilibrium in the local rest frame of the fluid. Yeah. So we want to solve this equation approximately. What we assume is that the relaxation time is small compared to the scale of space-time gradients. So which is basically saying that the Knudsen number of the system, which is a ratio of the mean free path to some characteristic macroscopic scale, is of the order epsilon. Epsilon is a small number. So this is basically rewriting the Boltzmann equation in this form. And then we want to solve this equation perturbatively. So we consider a perturbative series, which is known as the Chapman-Enskog expansion, and then solve order by order in this small parameter epsilon. Now, if we truncate to 0th order in epsilon, we get back ideal hydrodynamics that we were talking about. If we go 1 order in gradient, then we end up with the relativistic generalization of the Navier-Stokes hydrodynamics, where eta is a coefficient of shear viscosity that is related to the microscopic relaxation time that we have considered in the collisional kernel. So yes, okay, and these are some standard hydro notations. This is basically the velocity stress tensor. Now, one could have stopped here and tried to just solve this relativistic Navier-Stokes equations. But what turned out is that these equations are numerically unstable. The physical reason for this is because it gives rise to some diffusion type equation. Now, diffusion type equations are stable when we solve it, when we move forward in time, but it's not stable when we go backward in time. Now, what happens is, in this relativistic version, there are certain modes which travel faster than the speed of light. That means if we boost to a certain frame, these modes will travel backward in time. And that then we have to solve the diffusion equation as if backward in time, and which gives rise to numerical instabilities. So although we have a relativistic version of the Navier-Stokes, it is of no practical use because it gives rise to numerical instabilities. Now, the way to circumvent this is to first go one more order in gradients. So originally, the shear stress tensor was just consisting of this term, but now we go one more order in gradients via this procedure of Chapman-Enskog. But still, that is not enough because that does not solve this numerical instability problem. What needs to be done is the shear stress tensor has to be promoted to an independent dynamical degree of freedom. So in this expression, once we know the gradients, we instantaneously know what is the shear stress tensor. And this still gives us a framework which is numerically unstable. So then what is done is basically to rewrite this in a way so that we have a relaxation type evolution equation for the shear stress tensor. This was done by Israel and Stewart back in the day. Now, the main difference between this and this expression is that here we have essentially promoted this shear stress tensor as an independent dynamical degree of freedom. So in this talk, so this is the type of equation that is routinely used in heavy ion collisions to model the evolution of the coagulant plasma. Now, in this talk, I'll call this kind of evolution equation as Israel-Stewart type hydrodynamics, or ISH. So
how was it solved?
Yes, so what was done is, so basically this acausal modes that I was talking about is seen because if I write the dispersion relation for Navier-Stokes, I will get omega goes as k squared. If I just take the Navier-Stokes theory, take global equilibrium, linearize around it, and find out the dispersion relation, omega will go as k square. That means d omega by dk goes as k. That is why we said that the groove velocity of these modes are unbounded. It can grow arbitrarily high. What it does is this extra time derivative, it gives another factor of omega squared in the dispersion relation. So at large k, now omega doesn't grow as k square, but as k. So, no, this is not put by hand. So, in
you're writing with sigma dot as pi.
Sigma dot as pi dot.
Like self-force problem.
This is, like the telegraph equation.
Self-force problem is exactly.
Okay, I see.
There also you get non-physical solutions greater than speed of light.
Okay. So then this term tau r, this prescription is sort of regulator, right? It should not give new physics. But then the surprising part is when this kind of equation is applied, it seems that this works even when a system is far from equilibrium. So that is the main topic that I would touch on, that why does this trick, why does it suddenly extend the domain of applicability of hydrodynamics? Okay, so yes, so before going to an example where I'll
write sigma dot in this way and then somehow work it pi dot.
so because by using the first order relation.
So
that,
you take dot of that equation and the first.
Yes, so yeah. Okay, so before going on to look at a solution of Israel-Stewart type hydrodynamics, I will quickly say that using the Chapman and Skog expression, one can also solve for quantities that are not conserved, like the entropy current. And what we showed is that in a relativistic system, the entropy and energy need not flow along the same direction. I will not talk too much about it in this talk, but I'll just say it in passing. Okay, so around 2014, the concept of hydrodynamic attractor was discovered by Heller and Spalensky in a certain flow profile. So the flow profile is called Bjorken flow. It is applicable during the early stages of heavy ion collision, during the early stages of QGP expansion. The assumption is the fluid is homogeneous in the transverse plane, in the XY plane, and the medium expands boost invariantly along the beam direction. All that it means is there is no transverse dynamics, and the velocity of the fluid just is given by z over t along the beam direction. Now, this is best described in Milne coordinate systems, where these are the lines of constant proper times, and these are the lines of constant space-time rapidity. In this flow profile, the complicated partial differential equations of hydrodynamics, they reduce to simple ordinary differential equations. And what Heller and Spalensky looked at was essentially the evolution of the energy density and the shear stress tensor, which is basically given by this equation here, but reduced to this particular flow profile. So what they found is a very interesting feature. So here it shows a plot of this quantity pi normalized by the enthalpy density of the fluid to make it dimensionless. F is related to that as a function of the proper time scaled by the relaxation time, which appears here. So what they found is that this Israel-Stewart type hydrodynamic equation is being applicable. It doesn't break down and works even for very small initialization times, where the expansion rate of the system 1 over tau is enormous. So essentially, even in far from equilibrium regimes, this equation seems to stay quite reasonable. It does not give any spurious solutions. More importantly, different initializations of the shear stress, they seem to rapidly decay to some sort of universal curve. So this led to the paradigm of that there is an attractor in the Israel-Stewart type hydrodynamic theories. And then much of the interest was understanding why this was arising and why a certain, just a trick like converting sigma to pi somehow makes this theory applicable even at large gradient strains where hydro should traditionally break down. So there were So yes, so for example, if I plot the energy density, then I don't see any sort of universal attractor kind of behavior. So it only appears in this pi bar. Right. So I will essentially try to provide a physical reason why this is happening. The trick was going from sigma to pi. Yes. Well, of course, one must remember all that they demonstrated is that equation is not breaking down in far off equilibrium regime. This does not, of course, mean that this equation is describing some underlying fluid accurately. That one has to compare further. So lots of works in attractor to which we contributed a little bit. And what we asked is that when does hydro break down then? It should break down at some point. Right? So first guess was perhaps in Bjorken flow so Bjorken flow is controlled by the competition between the expansion rate and the interaction rate. So expansion rate is 1 over tau and interaction is 1 over tau r. Now at late times, what is happening is if we assume an ideal cooling law for the temperature or the energy density, then the Knudsen number, which characterizes how far the system is from equilibrium or how strong the gradients are. So that late times, the Knudsen number in Bjorken flow decreases, so the system thermalizes. But if the microscopic scattering rate was much lower, such that the Knudsen number increases with time, then our hope is, our expectation is the system will not thermalize, perhaps hydro will break down there. So what we did was, in this relaxation time, we parameterize it as a function of temperature and let this factor just grow with time so that the system cannot thermalize at late times. We worked with a certain variant of hydro, which is very similar to the Israel-Stewart hydro that I was talking about. Again, surprisingly, hydro still does not break down. So here, again, I plot the evolution of this shear stress normalized with the enthalpy density as a function of, in this plot, tau over tau 0, and here as a function of the inverse Knudsen number. What happens is, there are no signs of breakdown of hydro. It shows brief signs of thermalization before the system, again, because of the lowering of the scatter interaction rate, the system cannot thermalize, but goes back to a state of longitudinal free streaming. So all that I'm trying to say here is, even in this far from equilibrium dynamics, this Israel-Stewart hydro is not breaking down. So then we tried to understand what is this, how are deviations from this universal curve behaving at early times and late times, basically trying to understand better the nature of the dynamics near this, this magenta line here. So what we did is we just wrote down the evolution equation for this normalized shear stress. This cannot be solved exactly, but can be solved approximately by assuming certain time dependencies for the interaction rate. And so with this, so in that case, we managed to find out some analytical solutions. And the entire goal of this is to say that using those analytical solutions, we found out how small deviations from the magenta curve that I just showed, how those small deviations are damping far from equilibrium and close to equilibrium. So what one sees is that when a system is close to local thermodynamic equilibrium, these deviations damp off exponentially. But when the system is far from equilibrium, that is at very early times, then these deviations decay via a power law. But then at very early time, it is the expansion that is dominating over the interaction rate. So this rapid early time decay that was discovered by Heller and Spalensky back in 2014 seems to be driven not by interaction, but the rapid medium expansion at early times. So this was a hint towards what may be going on.
This
Yes.
time approximation is not also very good.
Yes, but in their analysis, they did not consider a kinetic theory. It was just hydro with a relaxation time. Now,
Is it valid in such a way? Probably that's wrong.
so whether the collisional kernel by RTA is valid, yeah, I think it is not valid, but still, even if there is some realistic collisional kernel that we take, that will differ from RTA in the way that the system thermalizes. But I think the generic feature that far from equilibrium, it is more or less non-interacting and close to equilibrium, that I think will still hold. So, yes. Okay. Now,
Is it possible to mathematically argue that that tree
Yes.
actually eliminates the causal solution? Just a mathematical property of that. It's not related to it.
yes, the acausal properties can be mathematically shown, but it has always been shown by assuming a system in global equilibrium. The perturbations around global equilibriums, it has never been shown for generic evolution of a fluid.
But doing this trick
Yes.
eliminate causal solutions, whether that can be shown mathematically. Like, some general properties of equations is responsible for it. It's not really very specific. That may be a possibility.
Yes. So, as I understand, this acausal behavior is obtained from analyzing the dispersion relations. That what is the group velocity of a wave if I compute? So d omega dk kind of analysis. So I know that for linearized perturbations around global equilibrium, that trick does reduce the upper limit of what the speed can be. But whether for a nonlinear system or not, that I think is yet to be looked at. So here, yes, that is true. Yeah. So then what we did is we looked at, so up to now all I have been saying is that hydro is not breaking down in far off equilibrium regimes. We have made no statement about whether in the far off equilibrium regime, hydro is accurately capturing the dynamics of the system or not. So here, what we looked at kinetic theory and obtained how the attractor solution in kinetic theory looks like. This is shown by the green curve. And here there are a variety of hydrodynamic Israel-Stewart type hydrodynamic theories, all of which differ by some values of the transport coefficients. And then we find that by slightly tuning certain values of higher order transport coefficients, the attractor of hydrodynamics very closely resembles the attractor of kinetic theory. So, which is saying that not only is hydrodynamics just not breaking down, it can also sometimes do a good job of describing of kinetic theory in far off equilibrium regimes. Now I will try to, then the question becomes, why is there an early time attractor in kinetic theory itself? Right. So why does kinetic theory show universality at early times? And what we did was, so till now, we are always looking at a system that has no bulk viscous pressure. So, or in other words, in kinetic theory, the system was considered to be massless. So what we did was, we introduced another degree of freedom, basically the bulk viscous pressure, or looked into massive kinetic theory. So the inclusion of finite mass gives rise to bulk viscous pressure. Now, Now, before we are only looking at the shear stress, now there is a bulk viscous pressure. And because the distribution function is never negative, the system has certain bounds that it should always follow. These are basically arising. All it is saying is that the shear stress and the bulk viscous pressure must lie within a certain region. And this region is obtained from the statement that the distribution function in kinetic theory can never go negative. So what we first, okay, this I will skip. So let us look at non-interacting kinetic theory in the collisionless regime. So we solve this Boltzmann equation in the limit of this infinite relaxation time or zero interaction rate. So in Bjorken flow, what happens is without interaction, the solution of this distribution function just can be given in this form. Basically, whatever is the initial distribution, the z component of moment of particles gets scaled by the time tau. What this physically means is whatever distribution function we start with initially, the pz component, the z component of momentum is continuously shrinking. Because of this shrinking nature of the distribution function, the effective longitudinal pressure of the fluid is approaching zero. So this is what we see in this plot. Whatever initial condition we initialize it with, if there are no interaction, the system, the trajectory is always moved towards a PL equals to 0 line. So basically, this is a feature. It has got nothing to do with interaction. This is just a feature of the geometry of Bjorken expansion, which drives the system towards vanishing longitudinal pressure. Now, if we now introduce collisions in the kinetic theory description and then plot the evolution of the bulk and shear stresses as a function of time scaled by the relaxation time, we see that there is no universal behavior in either the bulk viscous pressure or the shear stress tensor. So whatever Heller and Spalensky back in 2014 had obtained for the attractor behavior in the shear stress channel is now completely lost when we introduce a finite mass for the particles. So, and different initial conditions, they converged to each other only at late times where they're expected to merge because the system is approaching some sort of thermalization. So then the thing is, so what we saw is at early times, this non-interacting dynamics of Bjorken flow, it implies that the longitudinal pressure is vanishing. Now at late times, as the system is thermalizing, the ratio of this longitudinal pressure to the thermal pressure approaches 1. So this quantity, PL over P, has universal limits at both early and late time of the dynamics. So if we plot this PL over P as a function of proper time, then we recover the universal behavior that was previously seen for the massless case only in the shear channel. So essentially, kinetic theory has an early time attractor. And here we see finally that hydrodynamics, shown by the magenta curves here, are not doing a very good job of describing this early time universal behavior that is in kinetic theory.
So in kinetic theory, when you have massless particles,
yes,
conformal
yes,
that
yes,
is broken.
yes,
Massive.
yes.
This conformal symmetry had extra symmetries which gave the
Exactly. Exactly.
benefit that you had.
Yes. But this quantity, PL over P, if we plot even in conformal kinetic theory, then also we get this attractor back. So basically then what we realized is that it is the rapid longitudinal expansion of this Bjorken flow, which is taking the system towards PL equals to 0 at early time. This is a feature of the expansion profile and is independent of particles being massless or massive. Now, early time attractor for this normalized shear that was seen by Heller and Spalensky, it is driven by the same physics that we found when the particles become massive, basically the rapid Bjorken expansion. But what was happening is, in conformal systems, this longitudinal pressure and shear stress are just simply related to each other. They are basically interchangeable. So attractor in one just manifested as an attractor in another. So basically, this was the understanding of why we were seeing some sort of universal behavior in kinetic theory. So at this stage, we see that although hydro is an excellent agreement with far from equilibrium kinetic theory for conformal systems, description is not as precise when we move on to non-conformal case.
For hydrodynamics, why is it not matching?
So it is not matching. Okay. It is not matching because there are some shear and bulk coupling terms. So I think hydro is not being able to capture properly the coupling between shear and bulk
People derive hydrodynamic equation from kinetic.
from kinetic theory.
Then if I start from this two line kinetic theory, can I never reach this hydrodynamic equation from by doing movements on the kinetic?
Yes, but
This one is very different.
physics-wise, it's different. I mean, it's quantitatively different, but I think because even after that moment kind of analysis, we have truncated kinetic theory. So at far off equilibrium, the truncation plays a role. So that is why it's quantitatively different, but still, see, what we should expect is after tau by tau r of 1, that is where hydro and kinetic theory should more or less match. That it is anyway doing. But this second order hydro far from equilibrium is, yeah. So,
But anyway, it's also not matching at tau by tau over 1. Matching.
yes,
So then should I trust all of these calculations, calculate hydrodynamic equations from kinetic theory?
the thing is, we don't expect it to match perfectly at 1 also. Because all this hydrodynamics from kinetic theory, it is supposed to match when tau by tau r is considerably greater than 1, maybe 3, 2. So this result is not surprising. What was surprising is why it did so well before for the conformal case. So that is where it shouldn't have matched so well. But that I think is because of this extra symmetry that conformal Bjorken has. So, okay, so we didn't expect the theory to, this is still expected, but before, when, for example, this plot, this is a kinetic theory attractor, and this dots are kinetic theory, and this green is hydro. This is matching so well, even at very small tau bar. This is, in some sense, was a surprise. Okay, so we have at least one example where hydrodynamics is not doing too well, far from equilibrium. We looked at another example where the flow profile is like Bjorken in the longitudinal direction, but has some transverse dynamics, which is given by Gupser flow. The nature of this flow profile is that the transverse dynamics becomes so strong at late times that the system moves almost towards transverse free streaming. It cannot, the interaction rate cannot keep up with the expansion rate in the transverse direction. So here again, we see, so these green solutions are obtained from kinetic theory and the red ones from hydro. Here again, we see at late time, so here rho plays the role of the time. There is substantial difference between kinetic theory and hydro. And in fact, for certain initial conditions, we cannot even run the hydro code. It breaks down at the start. So another example where, No. Rho plays the role of the time here. Just the time. Just the time. Yeah. So here is another example where hydro is breaking far from equilibrium. So all of this suggests that perhaps we can formulate a new way of hydro which works even in these regimes where I have just shown that hydro is breaking down. So this I will talk in more detail on Friday, but I'll just quickly go over it, that how to formulate a theory that can work better than known formulations. So the way I see it is, whatever coefficients here, whatever these different theories are, I would say that this DNMR and third order, MIS is obtained phenomenologically. It has nothing to do with kinetic theory. But these two theories are obtained by systematically solving the kinetic theory. So given that, so this is second order and this is third order, given that these two are systematically coming closer, that I think is a satisfying way of getting to hydro from kinetic theory. But I can also take the path that you are suggesting, that just tune something so that reproduce.
Say, because they do have a better handle on the kind universal function.
Mhm.
If I know the kinetic function, I can get the hydrodynamic function just by integrating. Moment expect.
Okay, but this is one. So what about other initial conditions? What about, I mean, here there is, I have shown only the one curve, but if I have more initializations, then yeah. Okay.
If there are any further variations, but that's an easier access for accreditation, right? If you have a university.
Mhm. Okay, so what I was saying is that given that we have seen certain scenarios where hydro is not doing a very good job of reproducing far from equilibrium dynamics, how can we formulate a macroscopic theory that works better than traditional formulations of hydro? So the key idea is that Boltzmann equation can be recast as an infinite hierarchy of couple moment equations, where the low order moments correspond to the hydrodynamic quantities. So for example, the non-equilibrium part is bulk and shear. Now, for example, this bulk viscous pressure will now again be coupled to some other higher order moment of the distribution function, which itself will be coupled to some other higher order moment, and this series of coupled equations will go on. But somehow, to get some macroscopic theory whose degrees of freedoms are only these quantities, we need to truncate this equation or truncate the non-hydrodynamic moments that appear in these equations. Now, the truncation scheme determines the effectiveness of how the ensuing macroscopic framework will work. So what we thought of is, what is a least biased way of truncating? So basically, this is an inverse problem, that once we know what these hydrodynamic quantities are, what is the distribution function, so that I will use to truncate these non-hydrodynamic moments. So the strategy we took is, what is the least bias distribution that uses only the information provided by the conserved current? So that answer is that it is that distribution function which maximizes the non-equilibrium entropy of the system, subject to constraints that they also reproduce the instantaneous values of the hydrodynamic quantities, energy density, the isotropic pressure, the shear stress. So basically, this becomes a problem of using Lagrange multipliers. So the solution for such a distribution function, which we call the maximum entropy, because it is obtained by maximizing the non-equilibrium entropy, is given in this form, where these quantities in blue are basically the Lagrange multipliers corresponding to the instantaneous values of the hydrodynamic quantities.
Why do you use the maximum entropy part?
First of all, this is a non-equilibrium entropy, and it has, so this maximization is not related to any thermalization. Here, the idea is, given whatever I know, what is my least bias choice? That is the principle that we are taking here. That
Least bias choice.
meaning, say, it is the same idea that if I know that a system can be in various microstates for a given value of, say, energy, then the least bias choice is whatever microstate is consistent with this value of energy, I assign it equal probability, the microcanonical. Most probably, yeah.
Most probably distribution.
Yeah.
And most likely the distribution.
Yeah, that indeed. So, yeah, so
Not the bias. Most possible distribution.
yes, okay. I mean, yeah. So, yeah. Equal a priori probability, yeah. Yes, that is what I was just saying, that with if I know only the energy of the system, then any microstate which is consistent with that energy, I will not put any extra bias on one or the other. That is the sense in which I call it least.
That from that perspective, it is from
Ordinary English.
Okay.
The language that you are familiar with faster would be.
Next time you put slash most probably.
Yes. So I will discuss more about this later on Friday, but I will just show that using this principle, so this is some comparison of kinetic theory results with second order Chapman-Enskog hydro. The solid are kinetic theory and the dashed in all these are hydrodynamic results. We see significant deviation of hydro from kinetic theory here. The moment we use this maximum entropy principle, we see much better convergence with the exact solutions of kinetic theory. So this I will, yes. Yes.
What you're saying is.
So this is the evolution of the bulk viscous pressure. This is the evolution of, yes. And so this I will not talk too much today. Also, this maximum entropy principle can be used in heavy ion collisions at a different stage. So once the system is expanding and once it becomes very dilute, that hydrodynamics stops becoming applicable. So at that stage, the fluid dynamic degrees of freedom has to be converted to particle degrees of freedom. Now there again, we encounter the same problem, that given the fluid dynamic variables, what is the distribution function which we should use to convert basically the fluid variables to particles. So this is basically the problem of Cooper and freeze out. So again, the maximum entropy philosophy can be applied there as well. So I'll just, okay, and how much time do I have? 10 minutes? Yes, okay, I'll just, so now I will quickly go over an aspect of many body dynamics, which hydrodynamics always ignores, basically, namely thermal fluctuations. So I'll talk about how these fluctuations can be incorporated in relativistic hydrodynamics, whether they have any effects on final state observables, and whether they can be numerically simulated. So if we consider a system that is in equilibrium, then in any part of the system or a subsystem, the energy density fluctuates because of finite number of particles, and its fluctuations can be computed using standard statistical mechanics. Similarly, if I have a fluid in global equilibrium, even there, the velocity macroscopically may be at zero, but there are fluctuations of the velocity. Again, can be computed from statistical mechanics. Now in hydro, we never talk of this kind of fluctuations because we have the separation of scales, that the hydrodynamics So this is the length scale over which the macroscopic, this is the macroscopic length scale. This is the hydrodynamic cell size, and there is a mean free path. Also, there is a correlation length. So basically, in equilibrium, any two thermodynamic quantities, if we compute their equal time correlation function, it's given by, it decays, correlation decays, and where this decay length is the correlation length. This is always away from phase transition. Yes, yes. Now, because in hydro, we assume that this correlation length goes to 0, so 2-point functions must take some sort of form of given by Dirac delta function. So in hydro, we should have this 2-point functions of energy fluctuations. So this is like the specific heat, and then because we are assuming that the mean free path is, or the correlation length is vanishes, so there is no correlation between 2 points in space. Now, how to introduce this in what ordinary hydrodynamics we do? So this was for statistical fluctuations were treated long back by Landau, where the idea was if we consider a system whose macro state are labeled by certain number of variables, then the probability that these variables take a certain value is proportional to the exponential of the entropy. Now, if we consider small fluctuations about some mean, then the leading order correction to the entropy is quadratic because we are assuming it is in equilibrium. And then the 2-point function of these fluctuations can be obtained from basically knowing the entropy or expanding the entropy up to second order. Now, what Landau did was he recast this feature as a time evolving problem, basically writing the time evolution equations for these fluctuations. So there is this term which is like the drag term basically. So whenever there is some deviation from equilibrium, this term wants to bring it back to equilibrium. And then there is the stochastic noise part, which again, it's like a friction term. Exactly, exactly. Now, how is this noise specified? So the idea was the 2-point function of the noise or the autocorrelation function of the noise should be such that in equilibrium, we get back the 2-point function of this quantity that we have from ordinary statistical mechanics. So which essentially gives us what the autocorrelation function of the stochastic part of this equation should be. So as an example, we can look at the Langevin equation, which defines the evolution of a heavy particle in a fluid. So this is the term, is the friction term, which brings the momentum back to 0, and this gives it kicks. Now the 2-point function is related to this friction coefficient here. So essentially, we can extend this to hydro also.
This thermalization, this friction term is very important, otherwise it's never thermal.
Yes.
Even if you put in contact with heat gas, it will never thermal. Until unless your lambda sufficient large.
So saying that if I drop, if I, yes.
Use the friction term.
Yes.
And then this correlation function of noise follows this particular property that's come from this
fluctuation dissipation. Yes, yes. Basically, this 2-point function ensures this feature, that the equal time p square. This we know from statistical mechanics that this has to be true. Yeah. So we can extend this similarly to hydrodynamics. In hydro, the macro state is specified by energy density, flow velocity, values of the shear stress. And we also have computed an expression of the entropy till second order. Then we do the same formalism. Basically, this linearized approach, what should be the noise tensor and how it should reproduce the equilibrium expectations. And using this, what one sees is, so this is the familiar energy momentum tensor of usual hydrodynamics, where we have an evolution, the Israel-Stewart or type evolution equation of the shear stress. All one needs to do is to add a stochastic part to this, add a noise term here, and the noise autocorrelation function must be this, which we again obtain from the Landau method here. So what is the goal of all this? So now, because of the addition of the noise term, this term, all hydrodynamic variables are now fluctuating. Now, for small fluctuations, we can basically assume that there is some background solution, and on top there are some fluctuations of these hydro variables, and one can compute correlation functions. Now, if a fluid is in global equilibrium, then we already know what the equal time correlation function should be, because that is exactly how we deduce the autocorrelation function of the noise tensor here. So, for example, if a fluid was in global equilibrium, equal time correlation functions would be short-ranged because precisely of the nature of the noise. But for an expanding fluid, which is the case in heavy ion collisions, these fluctuations need not have attained these equilibrated forms. So essentially what it means is they can have some long range features, and which depends on the competition of the expansion rate and the equilibration of the fluctuations. So with that, if such fluctuations exist in a fluid, they should somehow make an imprint on the final state observables. So at the end of the hydrodynamic stage, these fields must be converted to particles via the usual Cooper-Frye mechanism. And then what happens is, so we can not only compute the mean values of this quantity, but also 2-point correlations of this quantity, which is driven by the 2-point correlations of the hydrodynamic variables. So what we showed here is the 2-point rapidity correlations as a function of the rapidity difference of final state particles using this framework of stochastic hydrodynamics. It turns out that there is some long-ranged features that thermal noise in hydrodynamics can give rise to, which can be seen in final state correlations of particles. And so now, yes.
Is it easy to say what mechanism?
Yes, all it does is, so if I have a little fluid element with energy density, flow velocity, all it does is it says what is the number of particles with a certain momentum. It gives the probability distribution of what is the distribution function of particles. So that is the job of this Cooper-Frye mechanism. It is, for example, if a fluid was in, this is the hadronization problem, but it is a very crude way of basically converting fluid to particles. For example, if the fluid was described by ideal hydrodynamics, this F, this distribution, would just be e to the power minus u dot p over temperature. So basically, if someone gave me what the local temperature is at a point and the flow velocity, I would just say, okay, what is the distribution of particles there? Now, so it has, no physical mechanism of converting the hydrofields into particles. All that it ensures is with this distribution, I would get back the hydrodynamic fields at that point.
Physical process when the collision takes place.
Yes.
There is a recoil, right? At the time of collision. So the QGP forms, is it basically a QGP just a resolved version of that singularity, or is it forming before the recoil and then continuing after the recoil?
So QGP is continually forming. Mm-hmm.
Right.
So
when it is approaching, right?
Oh.
So I'm saying that
Yes.
do you see within the QGP phase, do you see that effect, but there is a recoil? You are assuming that it is expanding. So,
yes, I think we don't see the recoil part.
you don't see that.
No,
So that means
no.
the assumption is that QGP forms only after that.
QGP, yes, that is the assumption. Yes,
Only after.
only after that collision. Yeah.
So those particles are relativistic. Those also happen.
So QGP doesn't form before that. Only after the maximum impact it forms.
Also, the
Otherwise,
recoil happens very fast. They're all relativistic.
it can happen very fast, but with QGP also disappears very fast. So
No, but that time scale is much larger than that. Those time scales are different because you're having transverse expansion, right? So there is no period number in that area.
so you are assuming that there is a transverse expansion while there is no contraction. When it is colliding, there is no QGP forming before the collision. That's an assumption, or is it?
No, that is true. That is because essentially the two protons go through each other, or the two nuclei go through each other, and they have gone on the loop. And what is expanding in the central area is the original nuclei are gone.
Yeah.
Right. Exactly. So they are colliding.
No, but they mostly
No.
go each other, go through each other.
Yeah.
So they are relativistic. It all flow.
Yeah.
Okay.
The lowest part of it, lowest part is here. Everything goes there.
Okay, fine. I got it.
Sorry, when you say particles, are these Thomson gluons or are they nucleons or some kind of generic particles?
These are hadrons.
Is that it?
Hadrons.
This is the end stage of
This is the end stage of hydro. Yeah. So. Okay. Yes.
It is hadron, right?
Yes.
That is not convoluted in the formula.
That is, yeah. It.
I mean, when I say baryons and mesons.
Yes.
And
Yes. This just distinguishes between particles based on their mass. That's yeah. It's a completely model. Yeah. Yeah. So.
Fair enough.
Yeah. So, okay. So finally, I'll just spend a few more minutes in just quickly talking about. So thus far, we have assumed that these thermal fluctuations are small. So, so linearized hydrodynamics is applicable. However, if a fluid is close to a critical point, then these fluctuations should become large and the correlation length should grow. So at this regime, the framework that I was describing should not be applicable because it does not account for either the growth of the fluctuations or the growth of correlation length. Now, this may have applications in the search of possible QCD critical point at finite baryon densities, which I will not go too much, but I will quickly say what the framework is that we are trying to formulate here. So let's assume that there is a conserved order parameter phi, which is conserved, so hence it satisfies this kind of simple equation. Now, if this phi is to describe a transition or dynamics near the critical point, then this it is governed by some free energy functional, which is given by the Landau-Ginzburg form. So this is essentially a time-dependent generalization of the usual Landau-Ginzburg approach. So the free energy functional is given by this form. So one just expands phi to higher and higher orders. So this kind of framework has been existing since way back, but the numerical solutions or the numerical method to solve it was still not there in the literature. So but this model is still rich because even with this simple model, we can get physics of growing correlation length or slowing down near the critical point and so on. So what we are working on is to use an algorithm based on Metropolis accept and reject method to solve for basically the time evolution of this conserved order parameter. So with this, I will briefly say that, okay, I'll just keep this details of this procedure. And in the previous case, this order parameter was just conserved. It has no coupling to anything. But if there is some hydrodynamics, and if we want to formulate some hydrodynamics near a critical point of a fluid, then this order parameter should be coupled to the momentum density or the velocity of a fluid. So which can also be done in this framework. So what we are doing at the moment is trying to formulate a framework which is stable and can solve these nonlinear aspects of critical dynamics. And but all of this is still in the non-relativistic version, and it has to be generalized to relativistic fluids. So I'll end by summarizing that kinetic theory provides an effective framework for systematic derivation of hydro. In flow profiles that describe the early stages of heavy ion collision, we talked about what is the physical origin of the universal behavior that was observed for kinetic theory. Entropy maximization provides a powerful method for deriving macroscopic theory, which is valid far from equilibrium. And stochastic hydrodynamics, which is not been explored much for heavy ion collisions, provide a novel way to test maybe the transport properties of QGP. And these are some open problems and long-term goals that search for non-equilibrium attractors beyond Bjorken flows in 3+1 dimensional hydro, or to work with a 3+1 dimensional stochastic hydro simulations to explore the transport properties of QGP. And finally, which I very briefly mentioned, to formulate a relativistic version of critical dynamics of fluctuations. So I'll stop here, and thanks.